types of generative models for regression. Now we're going to do a worked example with classification before we jump ship over to chapter 7, which will prepare you for this afternoon's lab. We have more people arriving. There are some chairs stacked there, so if people need to, maybe unstack them. Thankfully, the class has gotten small enough where I decided not to move us from our Tuesday location and time. The reason I didn't want to move is they said, great, we have a nice big room for everybody as long as we start earlier by an hour, if we start at 9. So I thought, well, we'll do that if we have to, but as it turns out, we don't have to. We're still pinched for space with the computer labs, so I will suggest a strategy at the end of today's lecture to cope with that. Let's continue with classification. So, we said we're going to try to deal with our measurements being some continuous univariate collection of numbers and our binary world in this case. So it's classification, not regression, so we just have two classes to worry about. Is that flickering? Does it? I just saw it sort of blink. Maybe that's just my imagination. Right. So a particular situation where you might have to do this is you might say, okay, I want to detect faces in images. The practicalities of this, maybe we'll talk about these more later, but just for now, assume that someone has given you a training set of images that are not faces. Someone's giving you a training set of images that are faces. So you have sort of the 0 and the 1 case. And your algorithm is going to run along, and for each pixel, it's going to center a bounding box around that. It's going to maybe a 60 squared box, and it's going to say, that patch of pixels, is that a face or is that not a face? And you will make some kind of classification. This is the world being in state 0 or world being in state 1, and we'll spit out some answer, and we'll move on to the next pixel, the next pixel, the next pixel, and thereby scan across the whole image. You might have to do this at multiple resolutions, okay, because faces might appear at different scales. So this is sort of not our focus right now for the moment. Let's just say we're going to look at a patch, and we're going to try to decide whether it's world state 0 or world state 1. We have some other examples detecting pedestrians in images, or you can also think of classification where you're trying to decide whether the test image is this particular person. So these are all data points that are supposed to be the same identity, right? The same person. All right. Let's get semantic segmentation. You're hopefully motivated enough now. You understand the problem we're working on. Right. We said the first type of model, discriminative one, we're going to try to make a probability distribution over the world state, and we're going to try to condition it on x, so we'll have some function of x that sits inside our probability distribution of w. If you recall, I had sort of this template where I said, I don't know about series, and I said, we're going to say, I want to model the probability of something given something else and theta, right? So we're going to do this by making a distribution on the A, that's something, and this will use a function of B to accomplish that, and it will also take the theta. Right. So in this case, we're saying the world goes here, let's write it in, world goes here, data goes there. All right. We did this for regression. Similarly, we'll do it for classification. The sneaky thing is that instead of having a linear relationship like we did with regression, remember linear regression? We said, we said we could have other types of regression besides linear, but we said let's make some kind of function, this function f here, that will sit there and make some kind of mapping between x's and w's. So if x goes high, that means that w's should be maybe low. So that would be a line sloping down. But here, we could choose to use a different function. So we're using this one called logistic sigmoid function, sometimes also called logistic regression. Unfortunate name here because it's got regression in it. Makes you think, oh, we're doing, no, let's focus on the logistic part, logic 0, 1, right? So what is this funny distribution that we're using? Remember, we have to have a distribution on the world. So we're saying we have a Bernoulli distribution. Bernoulli is good at having sort of two states, off and on. So we have a Bernoulli distribution on W, and our function of x is this sigmoid function, logistic sigmoid on x. It takes two parameters, phi 0, phi 1, and the second term is multiplied by x. So it looks a lot like our linear regression one, except that sigmoid splits out into this term, this equation, 1 over 1 plus the exponential of negative phi 0 minus phi 1 times x. Sounds like some bizarre function, and it is, and it's very, very cool. So what might happen is that you might get x's that are high and x's that are low. Data comes along, and whether they're high or low, for the Bernoulli distribution, you need the inside of this to be between 0 and 1. So what happens if someone hands you numbers that could be infinitely negative, 10 million, all the way up to infinitely positive, and you're actually expecting something between 0 and 1? Then it becomes very convenient that there's this logistic sigmoid function which has this sort of shape, where this is sort of 0 and this is 1. And the thing we're controlling with phi 0 and phi 1, as you might imagine, is where does this slope occur, right? We can sort of drag that over and have it happen here. And it's also affecting the phi 1 is affecting how slopey it is. So if it's very sharp, it might be a very sharp rise. So this intermediate zone might be kind of flat or very abrupt in some. So you can think of this is our x, right? We're putting in data here and reading off the logistic sigmoid of x here. Well, let's not do it that way, because we have to have our parameters phi 0 and phi 1. Okay. So logistic sigmoid to the rescue. We have our distribution, Bernoulli. We have our function, logistic sigmoid. We have two parameters, phi 0, phi 1. We have to learn them based on our training pairs, where we have examples of input data xi, and we have the world state at that moment, wi. Right. So just illustrating here, for different values of x, phi 0 plus phi 1 x goes right. Phi 0 plus phi 1 x will be this line, and then if you take that term, pass it into our equation for the sigmoid, this equation, right? Then you will get this kind of S shape. So what happens for w equals 1 is we have this sigmoid, and we're saying, right, the probability of the world being true for different values of x is now represented with this curve. Depending on phi 0 and phi 1, we can slide it left and right and make this flatter or sharper. Interestingly, for w equals 0, i.e. not a face, if these are our two classes, face, not face, it's just going to be the complement, so it's 1 minus the sigmoid. So, in fact, our job is kind of done when we just compute the probability of face, because we always know the other one is just the complement of it. All right. Two parameters. We can use them. We can learn them using a variety of techniques. And because this is a discriminative model, when we do this, we're done. We can, at test time, someone can hand us an x, and we can say, right, what is the probability of w equals 0 given x, and what is the probability of w equals 1 given x? We know they're complements of each other. Yes.
So if the world has 3 states, then if we found there's 2 of them, then can you imply the third?
The world had 3 states, then you could, and you knew for sure something about the first 2, then yes. Yeah, so now you're getting into a categorical distribution. You're saying, well, I know that the probabilities have to sum up to 1. So indeed, you only have to model the first 2 of the 3. Yeah. it tends to be that you do all three because you have uncertainty about the first two, right? And you have to sort of propagate that over.
Okay.
All right. Our second type, the generative one, where we just concatenate things together. Someone flagged this already last time. Can someone else see the problem with this? Now that we're doing classification. I think that's right. You have to speak up.
With continuous and discrete data, and it's kind of hard to concatenate them.
It's hard. There's no such distribution, right? So if you have a continuous vector x and you have a discrete w trying to make a single z that's sort of all the same kind of compatible units, it's not possible. So there's no obvious probability distribution. But we could do it. We could make a z like that, a bunch of discrete values, a bunch of continuous values. But then we have this task of finding a distribution for that, right? So there's no distribution like that handles sort of this mixed case. So in a way, this sort of fail. We say, okay, there's no sort of type 2 model for this situation. But not all is lost. We have second type of generative model, i.e. the third type in overall, the one where we are looking at the conditional probability of x given w. So it's a probability x comma w, x given w. All right, so same format as we've done before, right? Now we're going to find that we need some kind of probability distribution on the data. What's a good choice if you don't know anything else about it? There we go. Okay, so you don't need me anymore. We set up a probability distribution. We say there's going to be a normal distribution, a Gaussian on x, and it's going to take some function of the world state, and then compute the mean and the variance based on that. Now the world state is only 0 and 1. So in fact what happens here is that our function sitting inside of this is actually going to be fairly simple. It's just going to switch between 0 and 1. So we're going to say actually that we're going to have a class conditional distribution. Probability of x given face is going to be 1 Gaussian. Probability of x given not face is going to be some other Gaussian distribution. So if you had, for each Gaussian you have a mean and a variance, now we have 2 means, 2 variances. So our parameters that we need to learn in overall are going to be phi 0, phi 1, sigma 0 squared, sigma 1 squared. All right, so if we plot our probability of x given w, and so this is our generative model, we would say, right, for w equals 1, we sort of have 1 Gaussian on the x, and for w equals 0, we have a different Gaussian for the x. So their mean and their variance are free to change independently of each other. As long as we normalize at the end, right, then we'll be able to talk about real probabilities. So that means that we have to remember about Bayes' rule. Right? Life has given us this sort of lemon, so we have to remember that we have to multiply by the prior on the world state. Prior, you could learn that from your data set. You could say, well, I've got a bunch of images, and in them I've seen that faces occur this often, right? Maybe 1% of the time. Non-faces occur much more, so I'll include that here. And then for all of the world states, i.e. for both of them, right, we can integrate that to have a proper normalization term in the denominator. Right. This was our 10 to 1 or 100 to 1, right? Non-faces compared to how often we expect faces to happen. All right. So that's the end of our classification example. The question was raised at the end of last lecture by a few of you. Well, hold on, you're giving us all these choices. What do we do? How do we make these choices? How do we decide? It is a question worth agonizing over. So you should keep it in your mind when you're facing new problems. Things to consider: that generative models can be quite costly. So we've been dealing with nice situations where the data is univariate. The world state is one variable. Okay, great. But if you have data that is 50-dimensional, right? And your world state is only face, not face. It happens all the time, right? You might describe the pixels in the patch by all the intensity values in a 60 by 60 region, or you might compute the color histogram. You might say where are the edges. You might say what are the sort of dominant orientations. So we could quickly accumulate a feature vector, an x, that's 50-dimensional, right? Without trying very hard. But our output space is just W0 or W1. Having a 50-dimensional Gaussian, right? Having some sort of big distribution on X, right? Distribution on X, so i.e. a generative model, might be unnecessarily complex. Maybe the faces are all basically at this end, and the non-faces are all at this end. And the fact that the x's kind of go up and down, and there's this orientation, that orientation, doesn't matter so much. So this would be an argument when you have this dimensionality mismatch. This would be an argument to say, well, I just care about the output. The output is only 0 or 1. Maybe I should go with a discriminative model. Saves me effort also on the inference step. At the inference time, I don't have to depend on any kind of priors. On the other hand, if you have knowledge about priors, you might say, actually, I prefer the generative model because that's a good way of infusing that prior information. Other considerations. So I think I've mentioned that one already. Data really is generated from the world. So things like perspective projection and occlusion, right? If you say, well, I can see half a chair, right? Then what you're doing is you're saying, well, I know kind of how the world was generated. So now you can take that partial observation and say, what is the probability, given that the chair is in that position, so given the world state, what is the probability of observing part of the chair, given this layering of objects that are between me and it? So the generative model is sort of a very elegant way of representing what we already know about kind of the graphics pipeline of how things in the world are projected onto our cameras. Missing data. The generative model is able, I think I kind of gave that example with the chair, right? You might have some part of your feature vector X that you just don't know, right? I asked some kind of questionnaire of all of you, how tall are you, how much do you weigh, what is your favorite color, but I forgot to ask some of you what is your favorite color. I can still compute the posterior and say, well, assuming kind of the average for that question, I can figure out whether you like action films made in the 80s, right? Terrible example. All right. I think I already mentioned number 5. Okay. I think we're ready to not skin. I'm excited by applications, don't get me wrong, right? But I'm kind of on a timeline. So are there any questions about the mechanics of what we've done, sort of separate from the applications? Okay, all right. We will press on then. I will motivate chapter 7 by giving you this example. If you want to do background subtraction, this type of problem comes up all the time when you want to do segmentation. You want to say, I've got a CCTV camera, I'm observing a scene, I don't expect much to change in the scene except when somebody walks in or a squirrel comes in to steal seeds from my bird feeder, right? Pesky squirrels. I want to segment the foreground pixels, the moving pixels, from the background. So what I'm going to do is at each location, I'm going to try to say, I know what the color is of the pixel at that location, and if the color changes from that too much, then I'm going to classify that not as a background pixel, but as a foreground pixel. Right? So we have the world as 2 states, foreground, background. We could just take a single snapshot, and then we would find that actually the clouds come and go, that pixel gets brighter or darker, even when there's no squirrel involved. So, typical approach would be to say, well, I'm going to fit a Gaussian. I'm going to record video of this scene when I know there aren't any squirrels for half an hour, 3 days, whatever you like. And I'm going to make a big fit a Gaussian to each pixel location, right? I'll say this is the mean and this is the variance for the color intensity of that pixel. Then I can use that model to try to classify foreground versus background, right? problem is if you have something like this where there's a tree branch that sways. When it moves, you might actually find that you get some bright pixels and you get some dark pixels depending on which orientation the branch is in. It's not all over the place, right? You don't get ultra dark or sort of medium. You really only get these two distributions. But currently, we said, well.
Would that include your camera movement as well? Does that?
It could be your camera movement. It could be whatever reason you have that the data is coming in, that the data for the same class for world equals 0 is coming in two flavors, sort of two different clumps. And the point of this is to illustrate that fitting a Gaussian to this data would be a mistake, right? You'd realize, well, the mean, the expected value of this is wrong. It's never actually that color. In fact, there really are sort of two kind of distinct ways that the background can appear at that pixel, whether it's the camera shaking or something else. Okay, so we need something better. Now we're not going to throw away Gaussians entirely. We're going to move to mixtures of Gaussians. This is where we slip over to chapter 7. All right, so now you have the slides for chapter 7. And we have just enough time to motivate hidden variables and to explain mixtures of Gaussians sufficiently so that you can use them for your lab today. All right. Going to do this using generative models. We use discriminative models when we can, when it's appropriate. In computer vision, they do come up quite a bit, so we'll have a classifier chapter where we'll use them very heavily. For the rest of today, for today's lab, and for many sort of applications, if it's sort of unstated, we're going with generative models. In part, it's because we start with the sort of more thorough explanation of what's happening in the world, the model where we have more control, and then if we need to, we can always simplify. All right. So, densities for classification. We've already said this is our face example. We're going to continue with this same approach, but we're now conscious of the fact that a single Gaussian distribution, a normal distribution, may not be sufficient. In fact, so we've just gone through all this. We don't need to remind ourselves this is our generative model. We're going to use this one. And if we say, all right, I'm going to have a Gaussian distribution for class 0, right? That will have mu 0, sigma 0. Same situation for world in state 1. We have a different mean and variance. Now we can say, all right, I'm going to estimate those terms by splitting the data set. I've got my foreground and background pixels, or my face not face pixels, face not face patches. Separate them into two groups, and I'll train these parameters, the phi 0, so not face ones, on one subset of the data, and I'll train the other ones on the other subset of the data. Because they sit separately, right? These are normal distributions. We've already said that could be a problem if they are not actually Gaussians, if they're not normally distributed. So, I guess this is a further hammering this situation home, and it's also going to try to motivate hidden variables. So let's walk through this kind of step by step. We have 1,000 non-face patches, look like this. We have 1,000 face patches, they look like this. Each patch is 60 by 60 by 3 channels, so you've got a 10,800 vector. This is X, bold X. We'll say the prior on face not face is equal, right? We'll just fix that at 0.5 for now. If you fit a Gaussian distribution to your non-face data and another separate Gaussian distribution to your face data, as we've just described, right? For this particular problem, you get 75% accuracy when testing, right? Obviously, you test on a different data set than you trained on. So 75%, okay, not great. It could be improved. What's going on here? Well, there are a few things we can talk about in terms of pre-processing and how we organize it. Do we keep track of colors and so on? We're not going to dwell on that right now. Pre-processing is important. It can make big differences in your scores. But can we improve this accuracy just by changing how we model the distributions. One of the problems that we might see is when we fit these Gaussians. So here what we've done is we've said there are two classes, class not face, class face. If we can inspect what are the parameters after we've done the fitting. So this is the average, the mean non-face. This is the average face. And this is a plot of the diagonal covariance. So at each pixel, right, so we have this long vector, but we can always squish it back into the shape of an image. We can see that the variance is high everywhere, because these are bright pixels, for the background. In other words, there's not much in common for the background pixels. All the background patches are kind of all over the place. At all of these locations, there's a high variance. And for the face class, there's high variance around the edges, actually low variance. Can you see that in the back rows? Yes? So this is kind of darker. Can you kind of see the outline of a face? That's what you're supposed to see there in that image. That there is lower variance, that the lips seem to be kind of all in the same place. So we've managed to fit a Gaussian to the face situation, but it's not a very distinct looking face. And maybe we can do better. So some of you might have heard of mixtures of Gaussians. We're going to introduce them now. The idea is that maybe for a given class like face, we could actually cope better if we had multiple Gaussians kind of stacked on top of each other. Tomorrow, we'll also deal with the problem of outliers. If you had an outlier, someone mislabeled a patch, right, said this is a face when it's not, right, it could drag the entire Gaussian, the whole mean or the variance, far, far away from where it should be. So an outlier could really hurt your model if you're just doing a single normal distribution. And then there's the question of parameters, right? We said, oh, 10,800 variables in your X, and you're trying to make, let's say, a Gaussian. If you tried to have a full Gaussian, right, where there are parameters everywhere in the matrix, that would be d squared parameters, right, where 10,800 squared, but you only have 1,000 images to train on. You don't actually have enough training data to tell you what the covariance is between all the different dimensions. So we'll come back to that tomorrow. Today we're just working on this first problem, the first limitation. Right. So models with hidden variables, this is where we're working towards, and this is what you'll be doing in today's lab. I want to work up to this, so we'll see the slide again, but if it helps, keep in mind that we're going to be working with individual Gaussians, just like we've had before, individual normal distributions, maybe 3 of them here, and then we're going to sort of superimpose them together and say, actually, the probability of x for different values of x looks like this plot. It doesn't look like a single Gaussian anymore, right? It's got these multiple modes, so it can cope with things like moving branches, or maybe faces where people have glasses and people don't have glasses, things like that. These different Gaussians, right, are labeled as H1 through H3. This is going to be our hidden variable. We'll motivate that now. Keep this picture in mind. Different Gaussians, right, combining to give us a distribution that's sort of more complex than a single normal distribution. All right. This is the default case, probability of x. And we say, all right, I've got some hidden variable. I don't really know what it means for a branch to move or not move, but I'm going to expect that if there was a hidden variable that could say there are 2 flavors or n flavors or continuous flavors of why pixels are doing what they're doing, then I could integrate that out. I could say, well, I'll integrate out all the different versions of h. In the last picture I had 3 of them, and so I would be summing then, and then I'd be left with just probability of x. If I had this map, this joint probability of the x and the h variable. Though we can't ignore the parameters theta, right? The parameters theta, which define the parameters of our Gaussian, for example. So, in fact, once you include those, this is really the equation we're working with, And it's the same thing, right? It's just that we have to integrate out the hidden variable. So I've told you there's going to be a hidden variable. It may not necessarily have a physical meaning. In the case of mixtures of Gaussians, it has a physical meaning. It means which Gaussian do you belong to. All right. This is an illustration of a hypothetical problem where you have a variable, observed variable x, right? So we might have low values, we might have high values, but the hidden variable h, which in this case is continuous, it also varies from low to high. And it turns out that at different combinations of these, the probability can be quite high, hot here, or it could be lower in various other places. So this is our joint probability of our data x and some hidden variable h. Also sometimes called a latent variable, right? It's there, it's doing things, but we don't necessarily interact with it directly, and we will very quickly be marginalizing it out, right? Integrating it out, because we actually care about, remember, x and w. Those are the things we care about, ultimately. Expectation maximization. There's a nice proof of why expectation maximization works in the book. We're not going to go through the proof. We're going to kind of skip along through the highlights of what it's doing for us. We're saying that we have our probability distribution on our data jointly with our hidden variable, given some parameters theta. If we are given some training data, then we would like to learn what are the thetas. What are the shapes of those three Gaussians that we had plotted, right? Each of the Gaussians has some parameters. We would like to figure out which are the parameters that best explain our training data. Here what we're doing is maximizing the log likelihood, right? We all agree that's the same as maximizing the likelihood directly. The hidden variable is going to allow us to do this cool thing. It's going to say, actually, there's a lower bound. And let me illustrate the lower bound, and then we'll come back to the equation. The lower bound says, if there is a theoretical log likelihood of different values of theta, so here the x-axis is theta. I know theta is high dimensional, right? We said already, for two Gaussians, you've got two means, two variances. Fine, but if we could line up all the thetas in a row, we would say for all the different thetas, there's a log likelihood of theta, so capital L of theta. If we had this shape, we'd be done, we could go home. So what we do is instead, because we don't have it, we might talk about the bound, the lower bound. So this is this b function. And the b function is saying, I don't know what the shape of L of theta is, but at any time, the lower bound on the log likelihood of theta is this shape, this somewhat simpler shape. If I say that this is the log likelihood, this green shape, what I'm saying is I don't know how much higher the log likelihood is, but it is no lower than this green line. It is the red line. Imagine if we're doing this in practice, the red line doesn't exist, you don't know where it is, but you do know it's above this green line. So the lower bound is going to be useful because it limits the search. So let's come back here. We're going to introduce this lower bound, which is saying, right, for a distribution of the hidden variables, we are looking at the log likelihood of probability of the x and the hidden variable. We're integrating that out, and that is less than our log probability of the problem that we cared about initially. This is the problem we care about initially, right? Integrating out the h's, right? But this problem here is saying, right, normalizing by our qi's, these are these distributions on the hidden variable. This is going to keep us honest in terms of being always lower than the green line I showed. So the distribution, let's see, the h's, I illustrated those as being individual Gaussians before. H equals 1, H equals 2, H equals 3. If I have a data point, I don't know necessarily, a training data point, I don't necessarily know which Gaussian it belongs to. which is why we're going to have Q of H, because Q of H is saying there's actually a distribution, okay? H is this hidden variable. I'm sorry I had to introduce a hidden variable, but you're supposed to see that it's very useful because it's going to allow us to have mixtures of gases. The thing is, as soon as I have this variable, now I have to think about the probability distribution of the H. In the case of 3 Gaussians, it's going to be this categorical distribution that says, well, H could be 1, could be 2, could be 3, with various probabilities. So this is why Qi, for the ith data point of Hi, is saying this is the distribution of what H could be representing. Yes?
Sorry, so if we have, let's say, 3 Gaussians,
yes,
and we will have basically 6 in the phase vector will be 6 Gaussians, right? So,
yes.
So how big will H, how many variables? Is this up to you to decide how many you want to have?
H will only go, H will be a distribution over the number of Gaussians that you have. In your example, you said I have 3 Gaussians. So however many parameters a Gaussian has, okay, it has 2, fine. But however many Gaussians we're dealing with, we're saying H, this hidden variable, is going to be responsible for telling us which Gaussian it belongs to. So we only have 3 possibilities for H. It's a distribution over three categories. Yes?
So it's up to you to choose how, like, you have to look at your data first and decide, oh, this probably looks like 3 Gaussian.
Yep. There's a limitation slide at the end of this, which is exactly that point. So it's quite right.
Because like a different pixel have different numbers of Gaussian.
Yes. Different problem. Yeah, absolutely. We just think about it. The faces, right? We could say faces fall into 2 categories: people with glasses, people not with glasses. Backgrounds fall into 6 categories, right? Different weather patterns, day or nights. So it might be that you need different numbers of a hidden variable with different dimensions for the different conditional classes that you're dealing with, class 0, class 1. All right, so we're going to introduce the expectation maximization algorithm, which is going to alternate between the E step and the M step. Expectation, maximization. In each of these steps, we're going to fix one thing and adjust the other, and then we're going to switch, adjust the other, and fix the former. All right. So the E step is going to try to push that bound, that lower bound, up. So it's maximizing the bound with respect to our distribution on the hidden variables. The M step is going to try to maximize the bound with respect to theta. Back to our illustration. It's called the EM step, but this is M, this is E. Okay? Maximization, expectation. So the maximization step is saying, I really don't care about H. I just want to find the right theta, right? I want to find the right values of our Gaussians that will best approximate this unknown red curve. And so if I thought we were here, that this is the theta, the combination of thetas, that does a good job, we should update that theta and move over here. We'll talk about how to do that. There's an update equation for theta, because we'll be moving, think of it in time. This theta will initialize somewhere, like here, and then at theta, that's at theta t plus 1, so increment in time, right? We'll take a step and we'll move it forward. So we go from blue to pink. Once you've updated theta, so this is your M step, you've maximized with respect to some state of the hidden variables, right? So we fixed the hidden variables and we updated theta. Now you're going to take that pink point wherever you left off, and you're going to say, I'm going to fix theta now. I'm going to fix the variables. The Gaussians don't change, all right? But I'm going to try to do the expectation. I'm going to figure out what is this distribution over my hidden variables that best explains the data that I have given these thetas. So this will change the shape of the green curve, so we have a new lower bound that hopefully is better and better approximating the L curve. And we don't care about approximating the entire L curve, right? This is interesting. We want to approximate the top of the L curve. But we don't. We want to do this gradually and work our way up there. All right. So just explain that same thing. This is the same thing again in equations. The expectation step is saying, I want to update my distributions on H. I want to figure out which data point belongs to which Gaussian. Gaussians here correspond to different hidden variables. And for doing that, I'm going to fix my parameters. I'm going to just use theta at time t, theta time t, theta time t. We're not changing theta, we're just taking those fixed theta parameters and we're computing the conditional probability of x given some hidden parameters and that fixed theta times the probability distributions we have on our hidden parameters. For the m step, we're saying, oh, hey, we're going to update our theta now. We're going to change it from t to what we had at t plus 1, which means finding the best theta that maximizes this. If we had tried to maximize the whole problem without the hidden variables, we'd be fitting a single Gaussian. Or if we had multiple Gaussians, we wouldn't have a closed form solution for it. What you'll find is we have a closed form solution for this, and we have a closed form solution for this. What you should see is that when we initialize at theta t equals 0, so at time 0, we just drop a pebble somewhere in parameter space theta, and we say, right, let's start from there, and we will perform an E step, then we'll perform an M step, and an E step, and an M step, an E step, and an M step. So our lower bound will keep going up until it can't go up anymore. It also suggests to us a stopping criterion, right? When you don't see changes in your theta, you're not actually making any U progress, therefore you can probably stop. This is not guaranteed to be globally optimal. It won't give you a solution. It won't give you the ideal solution to the problem, but given this initial state, it will give you the local optimal. It will give you the local solution. All right, so let's do this now specifically for mixtures of Gaussians, but just tuck away for tomorrow that what we've been discussing so far is the hidden variables, the hidden variable being useful, us being able to do expectation maximization. It just so happens that when we do the mixtures of Gaussians, the H actually corresponds to this reasonably intuitive thing, which Gaussian am I dealing with? Okay? Please just remember that it doesn't always have to be so simple. The H can be more complex, can be more abstract than that. All right. So I've shown you this kind of picture before. Here we're saying, right? This is no hidden variable involved. We're just saying, I want to know what is the probability of x given theta. Right? I want a probability distribution on x. Because this is a generative model, I need to know the probability distribution on x. Of course, it's always conditioned on some theta. So it would be great if I could figure out the parameters theta. In this case, because we are saying there's a combination of Gaussians, we're going to do this sum of Gaussians. Right? Sum. We have k Gaussians, in this case k equals 3, and we're saying I'm going to have the first Gaussian with its parameters added to the second Gaussian, its parameters, and the third Gaussian. Except that each Gaussian is weighted. All right, so the total weight, the lambda here, lambda 1 plus lambda 2 plus lambda 3 has to add up to 1 because I want this to be a probability distribution. Overall, the weight of adding up all these 3 Gaussians should still be a meaningful probability distribution, right? You can't have a probability greater than 1 somehow. So the lambda k is playing this role of saying how much weight is going to each of the 3 Gaussians. If we wanted to do the maximum likelihood solution for the problem we've just seen without hidden variables, right, you would say, right, give me theta hat that maximizes this likelihood, this probability of x given theta for, sorry guys, yeah, thanks. I'm trying to do this quickly so that everybody has the whole picture for the lab today. So we've got I training examples, right? x1, x2, x3, right? And we're going to try to maximize this log of the likelihood, probability of x given theta. If you break out this thing and say, well, but that we just saw on the last slide, the probability of x given theta is this sum over our mixture of normals, our sum over our Gaussians, our weighted Gaussians. That's fine, you're allowed to do that, to go from there to there. But now you have the log of a sum. And so if you try to take the derivative of this new equation, set it equal to 0, and look for, and try to find the max of theta that way, you're going to be thwarted by this log of the sum. It's not going to get, you can't get a closed form solution for that. So we're going to try to do this iterative step, this E step, M step, back and forth, and we're going to do this subject to the constraint that our lambdas have to sum up to 1, and that our sigmas have to actually be sigmas, so they have to be positive definite matrices. So we have to impose these restrictions on our optimization, but we can do that. So the mixtures of Gaussians is allowing us to do this. So we're going to introduce the hidden variable. We're going to say the probability of x given theta and this hidden variable is a single normal distribution, right? But it's got the sort of h subscript here. So we're going to have as many of these as there are h's. And our probability of h given theta is this categorical distribution on h. We're saying, how many Gaussians are there? That's how many categories we have. All right. So if we write probability of x given theta, right? So this term essentially, it breaks out into this. We've got our sum over our k Gaussians. Probability of x and theta and h equals k given theta. This then can be expanded. Think of probability of a comma b given c, right? Turns into probability of a given b comma c times probability of b given c. Sorry, I'd write that down, but I hope it's clear now, right? When you have joint probabilities, we can expand them into a longer term with conditional probabilities. And we're going to represent this. We've already seen this. This is our sum over our weighted Gaussians. All right. So now this picture should make a little bit more sense. We're saying I'm going to have some Gaussians. They're going to have some parameters. If I sum them all up, if I weight them and sum them all up, this will be my overall probability distribution over x. However, I have to keep track of the fact that I have k Gaussians, and that for each k, this hidden variable is going to take a value. It's going to take a 0, a 1, or a 1, a 2, or a 3. All right. So I've already kind of said this. The hidden variable has a clear interpretation. Press on. Our goal is to estimate all of the lambdas, because we need the weights of the Gaussian, all of the mu's and all of the sigmas. The maximization, the expectation step is going to be changing how we think each data point is associated with a hidden variable, and the M step is going to be changing the parameters. Visually, that looks like this. It says, I have a data point here. It lands on the x-axis at this location. Right? So this is the same data point. It's the pink one. Given some parameters, theta, those thetas define two Gaussians. This green one and this red one. If I say, well, hold on, who's taking responsibility for this data point? Then we would say, well, the green is taking this much responsibility for the data point. The red Gaussian is taking this much, over twice as much responsibility for the data point. So the R is measuring that. The R here, the responsibility, is the probability that for the ith data point, the hidden parameter on the ith data point equals k. K equals 1 or 2, given that we fixed the parameters theta and that we have some fixed data point. Is this clear? This is fixed, this is fixed. We're looking at data point I, and we're just trying to figure out what's the probability that it equals, that it's associated with the first Gaussian, k equals 1, or what's the probability it's associated with the second Gaussian, k equals 2. That's our responsibility. And we repeat this procedure for every point, so we can compute the probability of all of the data points being associated with each of the Gaussians. So overall, for any one of them individually, right? I said this one has twice as much for red as it has for green. That's over twice as much as it is for green. But we will do this for every data point, and here they happen to be, the size that correlates to this responsibility. So bigger dots means more responsible. Yeah?
Just one question. The thing when you show the distances, the function values of the densities, it would be only if the priors were half-half, right?
If there was a prior that said, but we don't have a prior currently on the responsibility. We have.
Sorry, yes, the priors. I meant the lambdas.
Yeah. So this is So currently the thetas have given us these Gaussians. We are stuck with them for now, and so we're just computing the value of a Gaussian at this x location, this far away from the mean. And we're just reading off that value. So this is a completely deterministic step to say what is the height of this bar for xi.
Okay, or is the plot supposed to show that the densities were already multiplied by their respective lambdas?
These are already multiplied by the respective lambdas. That's the question. Yes, that's right. And I finally understood the question. Thank you. Right. For the m step, we're going to update our theta. We're going to say, I'd like to now, I figured out what the responsibility is between each point and each of my Gaussians. I'm now ready to do the m step. I'm going to try to maximize my parameters. I'm going to change them from the t version to the t plus 1 version. And the way we're going to do that is we're going to say, right, I've got this inner sum that's looking at the distributions over the h's and the log likelihood of the problem I'm working on. We can eliminate all the parameters that don't depend on theta, simplifying to this where responsibility plays a very big role. If you take the derivative of this, set it equal to 0, and solve first for the lambdas, then for the mu's, then for the sigmas, these are the equations you get. These equations are in your notes. There's also going to be an algorithm sheet for you to implement in today's lab. So we will be using this slide very heavily. We'll be using the responsibility calculation, and I'll just go forward. Obviously, this will update over time, E step, M step, iterate until no further improvement. And I just want to show you what that looks like in 2D. You might have the black data points. You initialize two Gaussians and say, all right, go. E step, M step, E step, M step. Right? E step, M step. Until eventually you see no change. The parameters of the two Gaussians aren't updating anymore. And you have one here and one here. This isn't always going to converge to the same thing each time. You have some control over where you initialize. Typically, it's good to reseed the process a few times. See if your Gaussians can converge to a place where you get a better log likelihood. You're not going to converge to the same thing each time, so don't even try looking for situations where they converge to the same thing. Instead, you're looking for the solution which converges to a better log likelihood. Your sigmas, this is the update equation for a full covariance sigma. So this is one example output. You could force your sigmas to be diagonal, right? So they're either horizontal or vertical, but they have just diagonal entries on them. So that's what this would look like. Or you could force all the sigmas to be the same, right? So fewer parameters to optimize, but then obviously it doesn't do as good a job fitting to the distributions. I want to show you, all right, this is the point about reseeding it multiple times, seeing where it converges. Eventually you get, maybe this one was the highest log likelihood, so you would keep that configuration. You would say, well, that's the best one. And we'll resume with the faces tomorrow. The idea is, though, the faces come out much crisper now. We have more flexibility than we did before. We have more parameters, so we had to do more work, but this is a better result than we had when we got 75%. Okay, now, if your name starts with, your surname starts in the first half of the alphabet, you get to go have lunch or dinner for an hour. and come back to the lab in Mallet Place Engineering at 4 o'clock. So you win. Okay? If your name starts in the second half of the alphabet, so let's say from N onwards, then you should go to Mallet Place Engineering 121, so it's the upstairs lab, and start working right away. Next week, we will flip this around. So